my screen.
It's a great pleasure to introduce Dimitris Koukoulopoulos from Université of Montréal. And you can start to speak, Dimitris. Thank you for coming to our seminar.
Muito obrigado pelo convite para falar aqui. Did I say that right? Yeah.
Obrigado.
For the invitation. So I'll speak about some joint work with Kevin Ford and Ben Green that we completed last year, and it's on the archive. So here's I'm gonna give, because this is a subject that a lot of people are not very familiar with, I'm gonna give a little bit of background. So here is the question in its most general, the most general setting you can ask it. So you pick an integer n, say between 1 and x, uniformly at random, and then you want to understand its multiplicative structure. And by this we mean we want to say something about how its prime factors are distributed and its divisors. And right, so you can think of this as dissecting the integer and then trying to understand what you can do with its parts. So sometimes this subject is called anatomy of integers. And here is a classic example. You take the prime factors of n, you order them, and then you put them at double logarithmic scale, and then when you want to understand the statistics of these, they behave sort of as if you just picked k numbers between 0 and 1 and you order them, and then you ask, well, do they lie in some region of the plane of the RK space? Okay, so this is not to be interpreted too literally, but something like that is true. And so in particular, what you can extract from this is that if you look at the jth largest prime factor, I should have normalized by log n here so that I make everything between 0 and 1. Okay. So if I had done this correctly, then what you can deduce from this is that the double logarithm of the jth prime factor is roughly of size j. Asymptotically almost surely. So I will be denoting this by AAS. And this means with probability that tends to 1 when x tends to infinity. Okay, so this is, prime factors are quite well understood. So let's see, what about divisors? A similar result is known if you put them at double logarithmic scale. Then you have, well, there are much more divisors, so they will be much denser. So you have log j here instead of j. But but this is, it's a sort of a lie if you just compare what I say here for divisors with prime factors, because the fact of the matter is that while divisibility by different prime factors are quasi-independent events, this is not at all true for divisors. So they're much more complicated objects to get your hands on. And one thing that is important is that if you put them at the logarithmic scale, okay, so by bracket k here, I mean the set of integers from 1 up to k, right? So these are my prime factors indexed. And so my divisors, of course, are in one-to-one correspondence with some sets, with sums of some of the primes. I guess I'm assuming here my n is square free. Let's assume n is square free for simplicity. And so right, so while point 1 maybe suggests well, that the DJs are sort of nicely irregular, the second point suggests otherwise, that because you have this ID structure, there should be a lot more interaction between them. And here is a classic heuristic argument from due to Erdös to see this. So let us consider the difference set, dn minus dn. And of course, these are ratios of divisors, and I can clear off the common prime factor. How many elements it has? About well, if I assume n squared free has exactly 3 to the omega n, where omega n is the number of prime factors function. So it has 3 to the number of prime factors of n elements. You can check when n is squared free. And because omega n is about log n, if you do the algebra here, this comes out to being log n to the log 3 elements. And all these elements lie between minus log n and log n. So you have lots of elements, a lot more elements than sort of points in space. And motivated by this argument, Erdös conjectured in 1948 that asymptotically almost surely, so almost every integer will have distinct divisors that are within a ratio 2 of each other. Because he said, well, there are so many elements that I have each interval of length 1 should get way more than 1 point. So maybe around zeros I have several points, and in particular I can find at least 1 point close to 0. Okay. And in general, it's not just about Erdös conjecture, but actually most of the interesting questions that we have about divisors are naturally occur at the logarithmic scale. So what we know about log dj is not enough. So one very well-known example is how many integers n up to x have a divisor between y and z. And this is a question that has been settled now by Kevin Ford, and it is related to another Erdos problem. This is the Erdos multiplication table problem. And this asks how many integers there are in the n by n multiplication table. And if you think about it, this is an integer n of size n squared. And really, most of the contributions should come when both factors a and b are roughly of size n. So understanding multiplication table problem really is counting how many integers up to n squared have a divisor of size roughly n. It's in a dyadic interval. Okay. And divisors are quite beasts that are hard to catch. Is Tenenbaum's result that says that this set dn does not have a distribution, even if it sort of appears nice and maybe naively you would expect it would have distribution, then it doesn't. And unless you focus on a subset of integers that has density 0, then you cannot have a distribution for the set dn. And what does this actually mean? Having a distribution would mean that there would be some, there would exist some probability measure mu, such that when I count how many divisors, let's say, lie in a subspace, in a subset of the space L, compared to the total number of divisors, then this could sort of converge to mu L. This can never happen. So these are irregular objects that are hard to get our hands on. It's hard to get our hands on them. And one way to see this is to so the dn is sums of log pi. So if I write log pi as e to the log pi, then I should have here, the base here should not be e, should be log x. This is important. Log x to the xi, and the xi's are the order statistics. But because the xi's are known the exponent, any tiny perturbation in the particular location of the xi's leads to very big perturbations, especially if you raise them to a logarithm of x, the exact location. So pinpointing the exact location cannot really happen. So it's a very singular distribution that this set has. Okay, so the subject of this talk is Hooley's delta function. So what is this function? So this function measures an extremal statistic of the set of divisors, of the distribution of divisors of the integer. So you take the set dn and you intersect it with a length of interval just counting divisors that lie between two consecutive powers of e to the u and e to the u plus 1. and you look for the worst case scenario. Okay, so this is an extremal statistic, so it's going to be potentially, it can behave very in a way that is very hard to pinpoint, because it's a very extremal statistic. And using this statistic delta n, we can reduce Erdős' conjecture, or we can restate Erdős' conjecture as showing that delta n is strictly greater than 1 asymptotically almost surely. And I put here the quotation marks, because in Erdős' conjecture the base is 2, and here the base is e, but that's not really so important. They're basically equivalent to each other. Okay. And Hooley's motivation when he introduced that at the beginning we have no relation with it and the theory of divisors, and in his paper where he introduced this function, he talks about connections to problems in Diophantine approximation and to Waring's problem. But I will not explain these connections, but they exist, and they're one of the reasons why delta Venn is such an interesting function. Okay. So what do we know about this function delta n? Well, the first major result on this was proven about this almost sure behavior was proven by Maier and Tenenbaum, who, right, remember that Erdős conjecture is just the first non-trivial lower bound on delta n. So just to show that there's at least 2 at some almost asymptotically almost surely. And they proved that Erdős conjecture is true, and in fact they could prove that it grows as some power of log n. And this is the power of log n they obtained in the first paper. It's h1, which is given as minus log 2 over log 1 minus 1 over log 3. It's some exponent that maybe the first time you see it is completely meaningless, but I'm going to explain where it comes from, so hopefully it's going to become clearer. But before I do that, the second result they obtained much more recently replaced this h1 by a better exponent h2, which has, instead of 1, it has 1 minus 1 over log 27, so it's a bit bigger. And also they proved an upper bound that is has an exponent log 2 here. And moreover, they made the conjecture that, as a matter of fact, the lower bound is the right size of delta n asymptotically almost surely. There should be an AAS here that I forgot. Okay, so this is the Maier-Tenenbaum results. Possible one, the lower bound, the way they used to, the argument they used to construct lots and lots of divisors close together. Okay, so right. So first, I'm going to explain to you some of the ideas that go into their work, and then I'm going to talk about some new work. So the first idea of Maier-Tenenbaum is really just taking Erdős' heuristic and trying to make it rigorous. So recall that what is Erdős' starting point? He takes this difference set, and that we can explicitly describe as this the logarithms of these ratios of coprime d prime. And Erdős' conjecture is basically can be restated as saying, as asking, what does this difference set have, does intersect in a non-trivial way the interval minus 1, 1. And because here we're trying to localize and find a very, very specific, cover a very, very, so Erdős' heuristic says that dn minus dn contains lots of points, many more than the number of intervals of length 1 that we can separate minus log n to log n. But this is not enough to conclude that it contains an element in a particular interval of length 1. Right, so the first idea of Maier-Tenenbaum was to use this additive structure of the set Dn, and the different set, of course, carries the structure too, as follows. So let me call Ln this different set, the Dn minus Dn, I call it Ln. And note that if I factor my integer as m times pq, where p and q are two prime factors, then, okay, this should be the other way, the inclusion. So Ln contains, in particular, it contains Lm, but it also contains some shifts. You take this Lm and then you can shift it around these extra ones. And in particular, Lm contains Lm plus this shift, log of p over q. Because this means that I can put p in d prime and q in d. This is what it means. And all the other prime factors of d prime and d come from m. So it's quite easy to see that well, if I had written this inclusion correctly, that it is true. Okay, so then the argument is now, okay, now let's say assume that Erdős' argument idea before was sort of accurate, that close enough to being accurate, that Lm is nicely in this sort of every part of the plane, more or less, gets its fair portion of points from Lm, now, not Ln. Then I can use this extra two prime factors I have to sort of move this around, move this set that is well distributed, and then just hit exactly 0. And then you can show that roughly well distributed, and second, that indeed with high probability, yeah, indeed they can find this p and q that they can shift Lm and then locate the divisor of Ln, locate an element of Ln between -1 and 1. So this is the first idea and the starting point of the paper. And the second idea is to take this idea and sort of, if you tensor it, it's by exploiting the fact that by exploiting again the multiplicative, this additive structure of Ln, and the fact that right, if I decompose my integer n into, say, j parts, n1 up to n capital J, then, and I locate a divisor, say, two divisors of n1 that are close together, and then two divisors of n2 that are close together, etc., up to nj, then and create a lot of divisors of n that are close together. So now Maier-Tenenbaum said, okay, forget about working with all the prime factors. We're gonna split the prime factors into sort of sets, convenient sets, and work with this with one set of primes at a time. Okay, so how many prime factors does nj have? Well, we know that because this nj is defined to be as the product of all primes in n from this interval, we know that the number of primes is basically the double logarithmic length of this interval. So it is approximately log of uj over uj minus 1. Okay, so then if you count how many elements you have then in L sub nj now, remember L is this different set of divisors, then this should be about uj over uj minus 1 to the exponent log 3. Okay, on the other hand, log minus log nj and nj, and because nj is the product of primes that are of size up to e to the uj, well, with very high probability, this it won't really be much bigger than constant times uj, constant times the log of the biggest prime factor. And this is because the prime factors are in double logarithmic scale in an arithmetic progression. If I take in logarithmic scale, they are in a geometric progression. So only the biggest guy should dominate the size of nj. Okay, so roughly lnj is contained in some interval of the form constant uj minus plus. Okay, so then let's repeat Erdős' argument, but now with these new cardinalities. What we need for Erdős' number of L and J to be bigger than the length of the interval that L and J lies in. So what you need is this relation between the parameters, so that your set L and J intersects, say, -1, 1 with very high probability. And if you do the if you solve this and optimize all the parameters, what you end up with is that you have to choose these checkpoints in this shape, this double exponential shape. It's e to the 1 over 1 minus 1 over 1 over log 3 to the j. And this, I don't know if you remember the statement of the first Maier-Tenenbaum result, but this is one of the constants that appear there. Okay, and then right, so then the largest of these parameters, e to the u capital J, should be roughly of size x. And if you solve what this means for J, it means that it should be roughly minus triple log of n over log of 1 minus 1 over log 3. We have 2 for each and J, and then so therefore for n I have 2 to the capital 2 to the J of them. And if I do the algebra, that should be an H1. This argument produces about log n to the H1 divisors close together. So this explains where the first Maier-Tenenbaum exponent comes from in the first theorem from their 1984 paper. Okay, and what happened in their second paper, in the second paper, the more recent one, they went back to their original paper and they squeezed even more out of it. So what they did was the following. So they said first, okay, let's use Erdős' construction to Erdős' idea that I described in this slide to find dj and dj prime. There should be a prime here. 2 divisors of nj that are close together. Okay, let's say we fix of the argument. They were using only the prime factors of nj minus 1. But now they say, okay, hold on, why should we just use these prime factors? We can also use the prime factors of nj minus 1, and we also have some more remaining prime factors nj if I divide through the primes I used in the first step, and etc. So at every step they have these extra prime factors that have remained, and they're gonna reuse them till they run out completely of prime factors. So there is this, it's less wasteful this step, and this is what this argument, and this is what led to an improved constant H2. Okay, so in our work with Kevin and Ben, we took a new point of view. So what is really the key idea in the main, at least in the and this is the key step in the second slide I showed you, the second Maier-Tenenbaum idea. What they proved is that if C is some fixed constant less than 1 minus 1 over log 3, and M is the portion of, sorry, this would be divisors of N. So M is the part of N that consists of the prime factors that are between e to the u to the c and e to the u. So if I take the logarithms, they're between u to the c and u. This is my M. And then essentially what they proved is, what was the important thing is to showing that the set dm has at least, so these are the logarithms of the prime of the divisors of M. So it has at least 2 elements within distance 1 of each other, asymptotically almost surely. E to the u to the c and e to the u, and then I get 2 elements, two divisors that are close together. just using those primes. So then we can also try and generalize this question, ask, okay, what about if we fix a bigger, any k at least 2, how small should a constant c be so that our set dm, where m is given, is this divisor of n, consisting of primes satisfying these constraints, how small should c be so that the set of divisors of m now, of the logarithms of the divisor of m, has at least k elements within distance 1 of each other, asymptotically almost surely. Okay, so this is a new question that Maier-Tenenbaum answered when k is 2. And let us call beta k to be the supremum of all set c. So it's the right. So this would be the best. We want to take and if I just repeat what Maier and Tenenbaum did, well, with heuristically at least, I should be able to show that delta n is at least log n to this power tk, where tk is minus log k over log bk, beta k. Right. So Maier Tenenbaum did this when k is 2. This is their first paper, their H1. But we can do it for any k, and maybe this gives us a better result. I don't, who knows? And I claim that, as a matter of fact, what Maier and Tenenbaum did in their second paper is secretly a lower bound for t2 to the r. So their idea, the argument of Maier and Tenenbaum can essentially be recast to prove that beta 2 to the r is roughly, as a lower bound, satisfies this lower bound. 1 minus, maybe there should be, maybe I think this fraction should be reversed. Anyway, it doesn't. 1 works. Okay, so this is roughly what they proved. And then if you plug in into this lower bound here, then you get this lower bound for t2 to the r. So I claim that this is what they did. If you view things from this new point of view. And taking this point of view and pushing it even more and trying to understand this question I posed here even more, led to our main result, our main new result. So what is our main new result is that delta n is at least log n to this new exponent h3, or asymptotically almost surely, where h3 is some constant, whose decimal expansion up to a certain accuracy I've written here. Okay, but from what I've told you here, you should already be suspecting that really what we did was to answer this question, or to give a partial answer to this question. So what we actually, with this theorem actually, that showed that this constant beta, if you take k to be 2 to the r, it's at least rho over 2 to the r plus little of 1, where this little of 1 is as r tends to infinity. And this rho is some explicit constant that is given in, I cannot write it down in a simple way. It is given in an implicit way. It is the solution of this system of this equation. So you have 1 minus 1 over 2 on the left-hand side, but on the right-hand side, you have this infinite sum and this 8j's, and this also involves rho, and these 8j's are defined in a recursive way that also involves rho. Okay, so just proving that this rho exists actually is a non-trivial task, and but it does exist, and so we show this in our paper. Okay. So this is the main result, and in the remaining of the talk, I will try to give you some ideas about where this Right, okay, so I should also say, again, gamma 3, I changed notation. Before these constants, I was calling them gamma, but now I decided to call them h later, and this is a remnant of the previous notation. So, so the conjecture is that, okay, this should also be an equality. So the conjecture is that delta n is equal to log n to the h3 plus or minus little of 1, asymptotically almost surely. So this crazy constant that you see here is actually the truth. That's what we think. Okay. So where does this constant come from? Before that, maybe I should mention for people who maybe they come from a more combinatorial background or from a more algebraic background, that these arguments can have analogies in two different settings, as it is two analogous theories for these are the anatomy of permutations and polynomials. So here we have polynomials over finite fields, and we define the analogous part of the Hooley delta function, which could be to count them to count divisors, monic divisors of f of some given degree m, and then maximize over m. So the analog of the logarithm is the degree in polynomials, for polynomials. And then the result transfers also to this, our arguments transfer to this setting, and we get the analogous result for this Hooley function as the degree tends to infinity. And the other analogous result is for permutations. So for permutations, the analogous notion of degree is the length of the permutation. Right, so the permutations dividing sigma is really the Hooley delta function counts how many fixed subsets, how many fixed sets does sigma have of a certain size. And we have the analogous lower bound.
Do you also have upper bounds?
No. And no, the only upper bounds for Hooley delta that are known are the ones that come from Maier-Tenenbaum. We don't prove the upper bounds.
And even for like permutations or polynomials, we don't have better upper bounds?
Okay, they have not been written out, but they can be proven.
That's very good, thanks.
You have to do the work then.
All right.
Adapting the Maier-Tenenbaum paper. I'm
No,
gonna
but I mean the right upper bounds. Like, can you prove a matching upper bound in the case of polynomials?
No.
Okay, got you.
It's equally hard. Will not help.
All right.
Okay. And actually, we work with them. We reduce all of these cases to one to a single underlying model problem, probabilistic model problem that I will explain a bit later. Okay, it's actually on the on the slide right after. So what is the problem is so the model problem that is underlying all of these different anatomical settings, integers, polynomials, and permutations, is this logarithmic random set model. Okay, so what is a logarithmic random set? This means that we construct a random set of the integers where we put a little a in our set capital A with probability 1 over a, and these are events independent of each other. Okay, so and let's let some parameter d tend to infinity. So then the analogous question in this setting would be, how small should we take a constant c so that there are k distinct subsets, a1 through ak, of our set A that only concern the parts of A between D to the C and D. Remember the U to the C and U, this is the analogous. The D is U here. Sorry, the U is D here. And so these k distinct subsets A1 through AK, this should also be A1 through AK, they have the same sum set. They have the same sum of elements. And the question is, how small should C be so that we're guaranteed to find with very high probability such k distinct subsets that have the same sum of elements. And with abuse of notation, I will be calling beta k to be the supremum of all such C, of all such C's. Previous question. Well, the analogy is that if I'm given a random square free integer n, then I can define A to be the set of those integers between 0 and log n. These are integers for which there is a divisor between e to the a and e to the a plus 1. So if I look at logarithmic scale, this is between a and a plus 1. And then if you think of what are divisors of D or rather logarithms or divisors of n, these are roughly, well, these are sums. These are sums of some subsets of prime factors. So they're sort of in correspondence with this set, because the log of p is basically a up to a small error. Then I can think of replacing log p just by this element here, a. And then I can think of divisors, or rather elements of subsets of A. Okay, that's a tongue twister. Okay, so this is the analogous setting, and this is the question we actually studied, and then deduced everything else from this model setting. Right, and there is a similar analogy for polynomials and permutations that I'm not going to go through. Okay, so how do we approach this question? Okay, so we want to solve this. We want to find subsets A1 through AK that have equal sum of elements. Okay, so this is, of course, a linear system of equations in the elements of A. And the goal is to solve this linear set of equations. But of course, the problem here is that there are variables A that maybe appear in A1 and in A. So we need to sort of break this, we need to break apart all the different parts and distinguish variables that appear in this or that part of the Venn diagram of the AJs. So in order to, so you can parameterize a Venn diagram in terms of vectors omega that are binary vectors. They have coordinates 0 or 1 and they're k-dimensional. And then the corresponding part of the Venn diagram, A omega, is the set of A's in A that lie in AI if and only for the index I, the omega I, the ith coordinate of omega is 1. Okay, so if you think about this for a second, then this is actually a parameterization of the Venn diagram that is introduced by the sets A1 through AK. And if I use this new notation, and I can rewrite this expression, sum of A over all omegas, over all vectors omega, of omega j times s omega, where s omega now is the sum of elements of A omega. And what is important is that these S omegas now involve completely disjoint sets of elements of A. So I can think of these variables. These variables are now independent. The variables in S omega are independent with the variables in some other S omega prime. So I can start doing a bit more linear algebra with them. And another thing I'm gonna say is that, okay, so what does this mean for all of these guys being equal to each other? It means that they're equal. If it means that if I form the vector of them, this is 0 modulo 1, where 1 is the constant vector with only ones, and terms of elements, because of this relation, can be written as the vector that is the linear combination of omega multiplied by these coefficients S omega. Okay, so this is a bit of linear algebra, just rewriting the problem in terms of this vector notation. And so now we only are dealing with a single vector equation now, which is a little bit more convenient notation wise. And also the coefficients here S omega, if we can solve for them and see how this relation determines these coefficients, then we have determined some of the elements A in our set A, just by solving this linear equation in vector form. Right. So the goal is understanding how does this, which elements of A does this equation determine? Okay, so the problem to eliminate any sort of dependencies, even after we have reduced to these S omega variables. And of course, the method to do this is to diagonalize the system. And when you diagonalize the system, you have to choose which variables you want to solve for, because there are many possible choices. And some choices will be better than others for understanding how well we can produce this, how efficiently we can solve this this set of equations. And remember that we need to solve the set of equations with all these S omegas being sums of elements of A that are constrained in this interval d to the c d. So, and we want to take c as big as possible. So when I say to solve efficiently, I mean I want to take this c to be as large as possible, so to have few variables. And the variables we want this system to be fixing should be as big as possible. And you can fix at most R of them, or exactly R of them it fixes, where R is the rank of the system. And each variable has a certain size with respect to the exponents, with respect to this, in this interval d to the c comma d. And let's say that the jth variable we are fixing has size roughly d to the cj. Okay, so this variable corresponds to some part of the Venn diagram. Okay, so to some of the vectors that we can solve for. And let's say that it has value d to the cj. And okay, so these thresholds cj are capturing how big are the variables that we can actually fix, that this equation fixes. And the diagonalization procedure that is the notion of a flag of vector spaces. And what is the flag is just a nested sequence of subspaces. And here I'm gonna, because we're working modulo 1, I'm gonna be insisting that the first one, the zeroth vector space, is the one generated by 1. Okay, so we have this one. Then okay, so how is this flag generated? So V1 is basically the flag that is generated by the first vector you're gonna solve for, corresponding to A1. And then V2 is generated by some other vectors, including the vector omega 2 corresponding to the variable A2 that we're fixing, etc. And And so when you do this diagonalization procedure, you create this nested sequence of vectors. And finally, there is one last thing that is important when you are trying to solve this system. We need to keep track of this, of how A splits in this Venn diagram. And really, what we really need to do is to understand the proportion of A that is the proportion of each part of the Venn diagram that is included between two consecutive thresholds. It turns out that this is a very important thing to keep track of, and it is captured by some probability measure mu j that lives on this unit cube 0, 1 to the k, and also it also supported on the vector space, on the j step vector space of the flag of vector spaces that we have. Okay, so there are too many things to keep track of, so we better give them a name. So this is the definition of a system. This is the definition of a system. So this C is the sequence of thresholds, and mu is the sequence of probability measures that keeps track of what portion of the Venn diagram is contained in each part. What portion of A is contained in each part of the Venn diagram. And okay, so right, so as I said, script V is an R-step flag whose members are distinct and spanned by elements of the cube. There is some non-degeneracy condition I don't want to comment really about. So C is the set of thresholds that are given like that. And mu is this R tuple of probability measures that satisfy this condition of the support. And okay, so this is just a system. This is just summarizing, just giving a bit of notation for what I explained in the previous page. And it's a very natural thing that occurs when you're trying to solve this linear system of equations. Okay. Is a combinatorial construction. So every time I fix these thresholds and these vector spaces and these measures, I'm sort of fixing a combinatorial configuration out of which I'm going to try and create k distinct sets by solving the corresponding linear system of equations. And the goal is to identify which systems are the ones that lead to the best possible values of C. And I claim that in this framework, the Maier-Tenenbaum is nothing but a construction of one particular system. So they just the one way, right? It's just a combinatorial construction that is really captured by this abstract and general definition. So you have these flags and these spaces and these measures. And Maier-Tenenbaum gave one choice that works. And to state our main results, I have to unfortunately introduce even more notation. So there is a notion, first of all, of the entropy of a subspace. So here we have a finally supported probability measure on Q to the K, and we have some subspace of Q to the K. Let's call it W. And then this subspace, right? When you quotient Q to the K by this subspace, it partitions Q to the K into some parts. Each part has a certain probability assigned by nu, and basically what you do is you calculate the entropy that this W partition, has with respect to nu. And so this is the entropy notion. Then there is the subflag notion, which is quite natural, which two flags are, one is called subflag of the other if all the vectors. And at each step, the vector space of, let's say, V prime, this is a subspace of the previous one, the other one. And then there is this e-value that is a very complicated notion. It's just, there is a way to explain it, but it would take too much time. It is what it is. It's just some linear combination that captures somehow the complexity of some sort of linear combination of entropies. It's very hard to give an intuitive definition of it, intuitive explanation of it. It is what comes out of the proof. So it is defined for every subflag. Okay. Okay, so I've copied it here, and it turns out that not every combinatorial construction, not every system is good. There are only certain very special systems, combinatorial constructions, that satisfy what we call the entropy condition. So the entropy condition is a bunch of inequalities on these entropies that say basically that for any subflag v prime of v, you have that the entropy of v prime is at least as big as the one of v, or this e value rather. For v prime is at least as big as the e value for v, and we say that there's a strict entropy condition if there is a strict inequality for all subflags v prime that are not v. Okay, and so roughly speaking, what does this condition ensure? That so when it's maybe some of you are more familiar with what happens, let's say, when you're trying to solve when you're trying to count points in a variety. You know, when you count points in a variety, potentially there are all these subvarieties that maybe have a lot of points, and in some cases give you a count that is bigger than somehow the naive upper bound, somehow the naive count that would come from the naive application of the circle method, let's say. And so the circle method somehow would only work if these subvarieties that had contributions that were smaller. And similarly, this entropy condition, if it holds, it's sort of saying that all these other different combinatorial constructions coming from subsystems do not have a contribution that is are not somehow better, and then we should have focused just on those ones. This is sort of, in a rough, intuitive way, what it says. And so this is what we need for our system to be a good system, so that it is able to produce k-distinct equal substance when we solve the system with high probability, the linear system. And the optimization find to determine the value gamma k that is a supremum of all possible constants c, for which there is a system whose last threshold value is c, and for which the entropy condition holds. Okay, so this, and then there is the gamma k tilde that is the same thing, where we need the strict entropy condition to hold. And again, intuitively, this just says take all these systems that are the we think are the nice systems, and use them to construct distinct divisors, k-distinct divisors. What is the one that is most efficient? And I keep saying that these are the entropy condition is the one that makes it, that distinguishes a good system from a bad system. And indeed, this is this theorem that says that this big K, which is the most efficient producing k-distinct sets with subsets with the same sum of elements, it's squeezed between this gamma k tilde and the gamma k. And you could think that then everything should be equal, because obviously gamma k tilde is equal to gamma k, because the only thing I did was change this inequality to strict inequality to one that allows equality. But unfortunately, this is a highly overdetermined system of inequalities, So it's not necessarily clear how we can go from one to the other. Okay, so this is some a technical but very annoying point that we couldn't prove the equality between gamma k tilde and gamma k. But this theorem basically shows that this definition, all these definitions I gave you about the systems really are and the entropy conditions really are the right definitions, and these are and it has basically reduced the problem of finding beta k to the problem of just solving this very concrete optimization problem about linear. And in particular, since the supremum, we can give a lower bound here to beta k by producing one very nice system that has all the desired properties and that satisfies the entropy condition. This is the hardest thing to do. So this is the restricted optimization problem, I should say. So as I explained, the entropy condition is so highly overdetermined that it's really, really hard to work with it. And but somehow, if you think about this problem, it is very natural to it's very tempting to focus, to just throw away almost all of these entropy conditions and only focus on some very, very special conditions that come from these very, very special flags that go up and then they just stabilize at some VM point. And we call this a restricted optimization problem. And we somehow think that it is if a flag that is good also satisfy the other one. It should satisfy the full entropy condition. But we cannot prove that. We can prove it in some cases, but not in all cases. And moreover, we can solve this optimization problem for very general flags, but again, not for all of them. And when you solve this, you naturally obtain some threshold Cj and some measures mu j. And we think that these measures that are produced are the optimal ones. So you just need to solve this restricted optimization problem to get the full one. And what is important here is that you have exactly as many constraints as you have variables. This is what allows you to solve this. It's not overdetermined anymore. And this is the flag that actually works. And this is the flag that produced a superior value to the Maier-Tenenbaum result. We call it the binary flag of order R. And it is k is a power of 2 to do the R. And what we do is that we identify q to the k with q to the power set of bracket R. So bracket R is the set of integers between 1 and R. Okay, and it's an R-step flag. And the vith component of it is the subspace generated by all the vectors x. Okay, they're indexed by subsets of R, of this bracket R, and they're set such that they're determined by their first I components. So they have dimension 2 to the I. Okay. So I think okay, so that's all I have to say. Thank you for your attention.
Thank you, Dimitris, for the nice talk. My dog is a little bit crazy here right now, so we have time for questions.
So let me ask, is there any structure in the set of d over d primes? By that I mean if you have d1 is close to d2 and d1 prime is close to d2 prime, then maybe you can multiply d1 and d1 prime together. I mean, yeah. Obviously there's some common factors, but I just wonder if it's a bit like a Bohr set. the set of solutions of close divisors?
So the board set would have a small doubling, or sort of small doubling, right?
Well, here, if you're looking at, I mean, one way to think of it is you're having a vector, which is the plus minus signs, right? So when you've got A over B, which is a product of primes dividing n, you can think of it as the product over the primes dividing np, some of the primes to the power +1, some to the power 0, and some to the power -1.
Yeah.
So if you like, you've got a +-1 vector that's, when you dot product it with log, is very close to 0. And then if you take two vectors like that and add them, even though they're no longer +-1 vectors, you're still going to be, when you dot product, you're still going to be very close to 0. So that sort of suggests that maybe there's some sort of lattice structure amongst these
From
things.
the ones that are very close to 0.
Yeah.
Yeah, okay. Yeah, but then the coefficients can vary. You can have coefficients that are 2, right? So
yeah, so part of this depends on when you get a typical pair D and D prime that are close together, do they use many prime factors? Because if they use very few, then you might expect very few coincidences in different Ds.
yeah.
You know what I mean?
Right. So that's why you do this decomposition into distinct to avoid this issue. Into you write n as a disjoint, as product. You split your prime factors into some disjoint sets, and then you look at what happens for one set and the other, and then you sort of add them.
So you are kind of using a basis in some sense. Just
oh yeah. This idea with the tensor product trick is using that. So you're using the fact that if you take n1 and n2 that are coprime, and you take this set for n1 and for set 2, then their sum set is inside the one for n1 and 2. So there is a structure like that, but it's more arithmetic because it has to have you must have the coprimality between n1 and n2.
yeah.
Yeah.
So I mean, this kind of works for my second question, which is when you've got this interval y where you get your loads of divisors there that are close together, y to 2y. How big is y compared to n typically?
So it's e to the log to some power, e exp of log to some power.
So it strikes me you could get some sort of upper bound. I mean, you could just take high moments, at least if you assume y is less than e, n to the 1 over log log n or something. You could take log log moments and get something.
So the argument of Maier-Tenenbaum is based on taking high moments for their upper bound.
Okay. I was just trying to think about Mark's question about how to get upper bounds.
Yeah. So it's definitely going by higher moments. Yeah, that's as far as I know, it's really the only technique we have for upper bounds.
I guess my point is, if you know y is small, then when you take high moments, you're going to get really the right answer, because when you use the Chinese remainder theorem, there's going to be no loss. It's only when y is large that your Chinese remainder theorem to a modulus that's bigger than n, and then you can't make it work.
Okay, but y is not fixed, right?
Well, that's my point. If you can prove somehow y, there has to be, if you had somewhere with a lot of divisors, you'd have to have a small y where there's lots of divisors, then maybe you can make that work. Yeah. By small y, I mean like n to the 1 over log log n. Anyway, it's just
there is an extra problem. It's when you use high moments, you need some sort of regularity for Helder to be efficient. Some sort of regularity of this function that counts how many you have between y and 2y. And I don't think this is a very regular function, especially when you go all the way to the extreme. The points where it attains its maximum seem to have seem to be very. I think they're very particular. They have some sort of structure between them, owing to this additive structure of the function.
So you're sure that there's not a almost always it's going to be for n, the size of delta?
Asymptotic to.
Well, I guess what you seem to be saying is delta n will vary quite a bit, typically.
Oh, you mean, I don't know. I mean, we cannot even pinpoint it within log n to the epsilon.
Right.
Yeah, right now we just have upper and lower bounds that are completely off.
No, I'm just saying just because we haven't got good techniques for estimating it, it doesn't mean it isn't a fairly smooth function.
Correct. I would be very surprised if it was so smooth. I would, yeah.
Yeah.
There are crazy things that if you take the average value of it, it does some very, very strange things also.
But I have to say, before Kevin proved his famous result on the multiplication table problem, I wouldn't have put my money that things would work out so smoothly.
What do you mean?
Well, you know, Kevin got this result up to a constant.
Yeah.
But before his paper, I've thought about that problem. I certainly wouldn't have thought that was true. I'd have thought it was more irregular. So the technique seems so hard and it's so difficult. You wouldn't think it would all work out so nicely.
Right. Yeah. And proving an asymptotic in that problem is also in Kevin's result, proving that it's asymptotic to constant times the order of magnitude he proved. That would also be very hard.
Yeah.
I don't even know if it's true. Like you, I'm very skeptical.
I have a more stupid question. So I just want to know what's exactly the input that you have from arithmetic. I mean, for example, if you're working with primes, so you only use prime number theorem to distinguish between the cases?
Sorry, we only.
So you say that you have this this model problem that you solve, and then you can apply it for the three cases, right?
Yes.
So what exactly do you need in each?
Yeah, you just need basically some sort of prime number theorem.
Oh, you need much less. You just need the sum of 1 over p, and from x to the theta to x is the correct asymptotic.
Yeah, some very weak version of the prime number theorem should be fine.
I mean, what you do elementarily.
I see.
But we don't. If I remember correctly, we only proved one way. Like the lower bound we have for the model problem implies well we want it. So in other words, anytime I give you right, so in this model setting, this A is this distinct A that has these distinct subsets with the same sum of elements, then I can produce a random integer that has this desired property, the corresponding desired property, and the random permutation and the random polynomial. But it doesn't work as perfectly the other way around. If you have a random integer, how do you actually go to this set? It's because you have this extra I explained here that you have this you have a little bit of noise. You're between e to the a and e to the a plus 1 for integers. It's not continuous, not discrete. So it doesn't work as perfectly. It would work much better for the other setups, for polynomials and for permutations, because there the length and the degree are discrete. Yeah.
There are more questions. Okay, so thank you very much, Dimitris.
Thank you for the
Well,
invitation.
it was a nice talk.
Very nice talk.